Okay, welcome to Submodular Functions Optimization and Applications to Machine Learning. For those of you who are here in person, this is a kind of strange for me to say this because I've already been talking to you for 10 minutes about other stuff. But in any event, this is June 4th. It's a big day for us here in Seattle because the Green Lake PCC has opened up. So I'm, right after this class, going to rush over there and buy some organic kale. I hope you all do that as well. It's a really nice thing to have here. So here are our readings. These are basically readings associated with submodular minimization, but now we have a whole... The bell I won't miss. The bell I won't miss. So now we have a whole set of other sets of readings, which are things that I've drawn from for today's lecture, including this nice survey article by Andreas and Daniel, and I can call them by their first names because I know them. And then Chandra Chakuri and Jan Vandrek and a bunch of other people, Minno, and we're going to be drawing from these sources basically randomly for the next lecture or so. This is something I don't need to do, but basically here we are down in lecture 19. Before I do that, I wanted to say one last thing about submodular minimization, so I'm lying actually. We're not going to talk about submodular min and max entirely. I wanted to mention a little bit about symmetric submodular minimization because it turns out that symmetric submodular minimization is a special case of submodular minimization, and interestingly enough, it's easier than general purpose submodular minimization. So basically, here's what we mean. So basically, we're saying f with this cup on top of it. We're going to use that to represent a symmetric submodular function. Now, symmetric submodular function means that the valuation at A is equal to the valuation at A's complement. So, symmetry is a concept that can mean a lot of different things. There are other forms of symmetry as well. What we mean is complement-based symmetry. And so if it's submodular and it's symmetric in this particular way, this is called a symmetric submodular function. But like I said, there are other ways that in the literature sometimes people refer to submodular functions as being symmetric. This is the way we mean here. And it turns out that we can essentially symmetrize any submodular function by adding its complement to it. So if you take any submodular function f, and then any value f of a, we add f of the complement, we've got f symmetric of a, which is a symmetrized version of the submodular function. And we can also not only symmetrize it, but we can normalize it. So if we take an arbitrary submodular function, and we add its complement, and then we subtract off the ground set, what we get is a symmetric submodular function that's normalized at the empty set if the original one is normalized at the empty set. Okay. And what we also do is we're guaranteed that such a submodular function is non-negative. And the reason why we get that is because if we evaluate f, the symmetrized f, so f cup of A, and then this is the valuation, right? And by submodularity, that's going to be greater than or equal to f of the intersection plus f of the union, which is equal to 2 f of the empty set, which is greater than or equal to 0. So therefore, f of A, f cup of A, is greater than or equal to 0. So just by starting with an originally normalized submodular function and symmetrizing it in this particular way, we're getting a non-negative submodular function. The other thing to note is that there's an equivalence class, because when we symmetrize it, we sort of cancel out any modular part of it. So if we started with we know that we can represent any submodular function as a Polymatroid function plus a modular function. But when we symmetrize that submodular function, the modular function, or any of the modular components, cancels out, and what we're left with is something that's equivalent to symmetrizing the underlying polymatroidal function. And the reason why is because the modular part, when we add this and we add that, we're essentially adding the modular part evaluated at E, and then we're subtracting the modular part evaluated at E. And so what we're left with is only the polymatroidal part. So therefore, symmetrizing, there's no difference between symmetrizing arbitrary submodular functions and polymatroidal functions. The other thing to note is, I defined earlier in this class, I believe, sort of the combinatorial mutual information function, which was defined in this fashion. And this, remember, just by the definition of submodularity, is going to be guaranteed to be non-negative. And so what a symmetric submodular function is taking the combinatorial mutual information function, just evaluated at A and its complement. Okay, so the combinatorial mutual information function is a little bit more general, because we are evaluating it potentially on A and B. But the symmetric submodular function means we're always evaluating it at A and A's complement. So B is always A's complement. Okay, yeah, and then, that's right. So mutual information, those of you who are information theorists, mutual information is obtained in this fashion. So the symmetric mutual information function in particular is obtained by setting the original submodular function, the non-symmetric submodular function, to be the entropy function. And we get mutual information. But in any form, as I mentioned earlier, in some sense, what the symmetric submodular function does is represent sort of the dependence or the information between a set and its complement. And in fact, if it's the case that the information, the combinatorial information between a set and its complement is 0, that basically means that there's a modularity, or there's an inherent independence, a combinatorial independence between any subset of that set and any subset of that set's complement. And we can say in some sense that F is decomposable in this way. And decomposable is a word that's often used in graphical models, and it's meant exactly in the same way here. And in fact, if the submodular function is used as an energy function for the graphical model, then it's exactly the same meaning. And so decomposable means essentially that if we take any subset B, that it basically decomposes. It decomposes into the part that's common with A, which is here, and the part that's common with A complement. Okay. So how do we prove this? It's actually fairly simple. We start by using, we represent B as the intersection with A and the intersection with A complement, and then we use subadditivity, and subadditivity holds whenever the sets are non-intersecting and the function is normalized. And so here's the subadditive property. So that it says that f of B is less than the f of the two components, or the two common parts of A and B with A and A complement. And then by submodularity, I want to get onto some other stuff, so I'm just going to skip all of these things and just go right to it. So basically, we use submodularity twice. So we start with this guy, and we use submodularity here and here. Okay. And then we use submodularity again, I guess by looking at here. Let's use a different color. Let's use, how about blue or something? So then we use it again. No, sorry. I wonder if it looks strange. Okay, here and here. So those are the two forms that we use submodularity. And then that basically gives us this last form here, which is equal to 0. Okay, because we've assumed that the function is decomposable in A and A complement. That's 19.5 is exactly the thing that we assumed on that previous slide. And so therefore what we've got is this subadditivity property, and then from submodularity we've got this. So therefore for any B, its valuation depends only on the intersection with A and modularly, additively, its intersection with A complement. Okay. So let F cut be a symmetrized version. And if it's the case that A is such that its valuation is 0, then A is called a separator. And you see papers, or old papers actually, on submodular functions that say things like finding the separator in a submodular function. This is essentially what they mean in this context. It's related to, but not exactly the same as, say, finding a separator in a graphical model. But there what one is trying to find is a set of random variables that render other parts of the graphical model conditionally independent. And in fact, there is a relationship to dependence here. And in fact, if A is a separator, then A and, say, B, anything not in A, is independent. And what we have in the submodular case is that if A is a separator, then if we take any subset of A and any subset of A complement, those guys are also going to be additive. That's the thing that we just proved. But that's exactly the analogous property to independence in random variables. If we have a set of random variables x of A and another set of random variables x of B, and x of A is independent of x of B, then it basically means that if we take any subset of the random variables of A and subset of the random variables of B, we also have independence. So now you can get that just by doing marginalization. You know, you can do that, and then you marginalize out some and you marginalize out the other. And after you've done those marginalizations, you still have factorability. But in the case of the submodular function, we're just doing that by the additivity of the submodularity in this particular case. Separators are closed under intersection, union, and complementation. And when you have that, and thanks to the fact that it's closed under union and complementation as well, means that separators partition E. Okay, so it's a partition of the whole ground set. Okay, so remember this, we have all these different definitions of submodularity, including this notion of conditional additivity, the conditional subadditivity, and all these other ones. We saw this a while ago, and we proved some of them. It turns out that, and here's a little bit of some historical anecdotes. When we minimizing symmetric submodular functions can be done in strongly polynomial time in n cubed time, and this is known. Actually, this is an upper bound. I think a lower bound is not known, but I think most people believe it's probably n cubed. I don't think there's a lower bound for this known, but this is the upper bound, obviously. And here's the algorithm, or part of the algorithm. So the algorithm is required to form a maximum back order, or what's called the maximum adjacency order. And this is an ordering of the elements. It's very, very different from the greedy algorithm. It is a total ordering of the elements, but it's not the greedy ordering. This is a subroutine in this algorithm that does the thing. And so what you do is you choose a V arbitrarily, you choose an initial element, and what you're doing is you're creating a list. So Wi is going to be the chain. Well, it's actually not really a chain. I think of it more as an ordered list, because you're not really necessarily creating a chain of sets like you do typically in the greedy order. What you're really doing is creating a list of lists where the next list has got a new element appended onto the end of it. So these things are ordered. When you're creating a chain of elements in the greedy ordering, it's like each one of these sets are not ordered. But here, what you're doing is each one of these are in some sense ordered sets or lists. And so what you do is for all remaining elements, you choose the next element that minimizes this gain. So it's the gain of, it's this thing that has the smallest gain of adding U to the previous list, okay, which might be negative, amongst all of the elements that you haven't yet chosen, which is down here. And then when you choose that guy, Regentais arbitrarily, you just append it onto the previous list and create a new list. Now here's something that I truly find fascinating. Actually, no, this isn't. I don't find this fascinating. The next bullet point is what I find fascinating. But this bullet point says that notice that the function operates on, the way Kiran, and it took me I think 5 years to pronounce his name properly. Kiran is I believe how you pronounce his name. So anyway, Kiran's the way he's defined it is that basically F, you start with the non-symmetrized version of F. But if it is the case that F is symmetrized, then of course it's the same anyway. But these max backorders is defined based on the original F, the non-symmetric version. But the thing that I find fascinating, no, this isn't what I find fascinating either. Okay, so I will tell you when the bullet point arises that I find fascinating. It's not this one. But what this one says is that the last two elements actually, as we will see, serve as a surrogate minimizer for a special case. And it turns out, so what we're going to do is we're going to repeatedly find these max back orders. In fact, you can see that this is an n squared problem right away. And we're going to run this thing n times. So that's going to give us the n cubed thing. And then each time we run it, we're only going to use, out of this long list of length on, we're only going to use the last two elements. And it turns out that the last two elements act as a surrogate for a minimizer that contains the last element and not the penultimate element. Not the second to last element, just in case that word is unfamiliar to you. Anyway, so what those two last elements are called is called a pendant pair. Now, pendant is sort of like you know, you've got something like this, and you've got like a pendant, like a maybe like a hanging clock or something. Sorry, that's not a clock. Like whatever, you know, 1, 2, 3, 4. So it's a pendant pair. So it's like it's a pendant, it's hanging, and T is a pendant pair if U is a minimizer amongst all sets that separate U and T. So what does that mean? It means that here you're basically considering all. Sorry, there's a missing guy here. So it's A, which is a subset of V. So you've got a bunch of sets, all of which are minimizers of the symmetric submodular function. But they're minimizers under the constraint that U has to be in A and T is not in A. And so this ordering matters. TU matters. So U, the position of T, this is, when you use parentheses, that's an ordered list, right? So you're talking about U being in the minimizer and T not be. And it turns out that the max backorder actually gives you the pendant pair. So what this means is that F of U, that singleton element, is less than or equal to F of A for any A that contains U and not contains T, if it's a pendant pair. And you can sort of, the reason the terminology pendant pair comes from the fact that if you think of it as a graph cut, because remember graph cut is a symmetric submodular function, what you end up getting is that you get, there's some really interesting properties about graph cuts that it turns out that even though you can have very, very many different cuts, you only have n-1 different possible evaluations of the min cut. And strangely enough. And there's a structure which I'm not going to talk about today called the Gomori-Hu tree, which can actually represent, since it's a tree with n-1 edges, it's a tree over n nodes with n-1 edges, you can actually represent all n-1 valuations of min cuts by essentially replacing the corresponding edge with the valuation of that min cut. It turns out symmetric submodular functions also have a Gomori-Hu tree. And what happens in the graph cut case, and the reason why it's called pendant pair, is because that U, when you construct a pendant pair, it is sort of in the graph something that's kind of hanging off in a pendant-like fashion. So, I don't know. Names. What would we do without names? Now, the theorem we have, which we're not going to prove, but there's a nice proof in Caron's paper, shows that this ordering by the maximum back order or the maximum adjacency order algorithm is a pendant pair. So the last two nodes. And now we do all this work. We do order n or n squared work, and we're only getting two vertices, or two elements in the ground element. And then we throw away everything but those two. So it's a lot of work for a little bit of benefit. But here's the fascinating thing. Okay, finally. So does anyone know anything about graphical models? So if you don't know anything about graphical models, you should take my graphical models class, which is going to be offered in the fall. But in which case, we will learn about things like chordal graphs and triangulated graphs, and testing chordality, and a famous algorithm by Tarjan, who's a famous theoretical computer scientist, for testing chordality is fairly easy. And there's an algorithm called the maximum cardinality search, which can very cheaply test if a graph is chordal or not. Now, chordal graphs, by the way, are the graphs for which there exists a junction tree, and the graphs for which there exists a junction tree are the ones for which you can run leaf propagation and get exact solutions. We'll talk all about that next quarter. But the interesting thing is that this algorithm, this maximum backorder, is exactly the same algorithm as the maximum cardinality search. It's the maximum backorder. And what it's essentially doing is basically finding elimination orders in the graph in reverse order. Strangely enough. So no one, I think, has really made that connection. I mean, between what is it about this that's properly and efficiently testing chordality, and what is it about this that's such a fundamental part of minimizing symmetric submodular functions. But I just have this belief that there's a fundamental connection there, which is currently unexploited. So minimizing symmetric submodular functions. Now, once we've got a pendant pair, there's two things that can happen. One thing that can happen, let's say that that x star is the true global minimizer of the symmetric submodular function. So one thing that can happen is that if it's the case that U is contained in the global minimizer and T is not contained in the global minimizer, then then in some sense U acts as a global minimizer, right? Because U is as good as that global minimizer. Because if any global minimizer that has U and not T, which would mean necessarily by the pendant pair property of the pair TU, means that U is also a global minimizer. But if that's not the case, if the global minimizer doesn't have that property, meaning that the global minimizer either has both TU in it, T and U in it, or neither T nor U in it, that means that we can essentially then sort of create a new problem where we've grouped, I think I've got a slide for this, where we've grouped T and U together to create a new ground element. So what we do is the following. We say, okay, well, whatever happens, we find the evaluation of U, since we know it's a pendant pair, and we store that minimum value, and then we create a new problem, because we don't know if that's the minimum problem or not. We don't know what the global minimizer is, but here's how the algorithm works. We go ahead and store that value, and we store U, okay? Because if that value ends up being the min, then U is going to be the minimizer. And then what we're going to do is we're going to create a new problem, new instance of the problem, a slightly reduced version of the problem, where the two ground elements, the two elements corresponding to the pendant pair, are grouped together to create a new clustered element TU. And we're going to replace the elements T and U in the ground set by this new element TU. Now, I'm very lucky I didn't call it the first T a P, because that would have been a very funny name to call it, but that's a very ridiculous joke. I don't know why I said that. Anyway, so we have this new ground element, no risk, no reward, right? So if you don't go out on a limb and occasionally make risky, ridiculous, really stupid jokes, then none of the jokes are ever funny. But occasionally you say a joke that is kind of like grown, only occasionally, right? Not frequently. Okay, anyway, back to this topic. V prime is the new ground element, and we create a new symmetric submodular function which is defined on that new ground element. So what that new symmetric submodular function does is the following. If you've got a set X that doesn't contain this new element in it, you just evaluate it based on the old submodular function. But on the other hand, if you've got a set X that contains TU in it, then you basically then you evaluate it by removing the new element TU and sticking back in the old elements T and U to get the valuation of this new submodular function there. Okay. Now, it can be verified that this is symmetric. And then what we do is then find a new pendant pair using the maximum adjacency ordering algorithm. So this is the step. Like we construct this submodular function, and then we run another n squared sweep on this new function. Now, of course, the ground element, the ground set is of size n minus 1, but we still think of that as order n. It's an order n prospect. And we do this n times. And so each time we do it, we get a pendant pair, and we store the min. And then what we do is we find the minimum of the min of the pendant pairs. We take the minimum over the u's. So that there's going to be some pendant pair, let's say it's T prime and U prime, which is going to be the min. Now U in general, remember what we're doing is we're grouping together elements. So the whatever one we end up finding, the pendant pair that we end up finding, might very well be a very large group of original elements. But whatever that is, U prime, the group of elements in the original problem corresponding to U prime in the reduced problem, minimizes the symmetric submodular function guaranteed. And that's the algorithm. It's pretty neat. And it does so, as I said, in n cubed time. So now here's a little bit of historical anecdote. So this is something I've gleaned from talking to people and reading papers. So in the 1960s, Jack Edmonds sort of defined the notion of submodular functions. Then in the 1970s, the whole theory of NP completeness came out, and there was a concerted effort by people like Laszlo Lavas and a lot of other, Shriver and a lot of other smart people to try to come up with a proof that submodular function minimization was polynomial in time, or to prove it was NP complete. And a lot of people, as you know, if you look at like Johnson's book, I mean, there was hundreds of problems in the 70s. Basically, the 70s was a decade of this problem's NP-complete, this problem's NP-complete, this problem's NP-complete. And then, basically just within a few years there was just this explosion of problems that were discovered to be NP-complete. It was amazing. It was a very exciting time in the computer science theory community. Submodular function minimization was, of course, one of the ones that was considered. It wasn't until the ellipsoid algorithm came out in around 1980 that we talked about, proved that submodular function minimization was not NP-complete, it was polynomial time. But that was the ellipsoid algorithm. The ellipsoid algorithm is very difficult. It's not only continuous, but it's just hard to optimize. It has numerical sensitivities that are difficult to control. And so for the longest time, for about 15 years, coming up with a combinatorial, strongly polynomial time algorithm for submodular function minimization sort of went unattempted, or maybe there wasn't as much of a concerted effort. Like once it was found that it was polynomial, there wasn't as much attempt. It wasn't until Kiran in 1995 showed this n-cubed algorithm for symmetric submodular functions. And then that spurned effort over the next 5 years, which led to the sort of, I think they won Fujishige and Shriver, they won a major award in the mathematical programming community for coming up with the first combinatorial, strongly polynomial time for submodular function minimization in around 2000, Lisa Fleischer and a few other people. But of course, what's not known is whether or not it's possible to do general purpose submodular function minimization as fast as symmetric submodular function minimization. The problems are not equivalent. In fact, suppose you wanted to do symmetric submodular function minimization, but insisted that, let's say you have two elements, and you insisted that I want to find, it's kind of like the difference between ST cut, right? You want to make sure that in the minimum it's got S but not T. Or since it's symmetric, it's the same thing if you insist that it's got T and not S. So you add a constraint. As soon as you add that constraint, then symmetric submodular function minimization becomes just as hard as regular submodular minimization. So that seems to suggest maybe that symmetric submodular minimization is somehow easier, because it's like unconstrained general purpose submodular minimization. And now, it's still the case that nobody really knows how simple general submodular function minimization, but I think, as I mentioned before, when I spoke to Fujishige in 2012, the direct quote was, he hopes that general purpose submodular function minimization is n to the fourth. And from the results that I talked about last time, at least it's not a proof, those results. It just sort of says, well, at least for this range, it doesn't seem to be n to the fourth. That doesn't mean something is going to change when it gets bigger. Empirical results, it's really hard to say anything about asymptotic complexity with experimental runs. Okay, if there are any questions about that? Actually, since the next thing is going to be a topic change, maybe I should just, maybe I should take a break now. But are there any questions before we take a break? By the way, I should mention that, symmetric submodular function minimization is very useful for clustering applications. And in machine learning, there are some really useful clusters. Like even, for example, things like clustering random variables based on the mutual information function. You want random variables to be within the same cluster if they're very, very strongly related to each other, and you want them to be statistically related to each other, and you want them to be in separate clusters if they're not statistically related to each other, if they're either independent or almost independent, or if they're only loosely correlated. And that's the reason why you might, in information theory, you might want to do that because you want to jointly encode variables that are strongly dependent on each other, and it's not such a big deal if you don't jointly encode random variables that are not strongly statistically related to each other. And so therefore that's a reasonable goal for clustering. Or for example, like feature dimensionality reduction. Like maybe you take a set of variables, features that are strongly related to each other, you reduce them to a low dimensional subspace or something, and then create a feature for that. There's lots of applications for that, since these bundles of things don't interact statistically. But then, of course, that's true of any Polymatroid function as well. You can cluster the ground elements. Okay, so let's take a break and come back. Now this is the big test. Is it going to crash? Let's see. Okay, so, maybe it's obvious, but in this class we've spent a lot of time on structures and the polyhedral approach to submodular function minimization. There's also a large amount of applicability and utility and intrigue associated with submodular function maximization. And it's useful for a variety of reasons. As I've mentioned in the very first lecture, there are problems like sensor placement and facility location and document summarization, or any kind of problem where you sort of want to cover, you want to sort of choose a diverse set, or any of those sorts of things, come up with a representative subset of some large set, any summarization kinds of problems. That's all basically based on submodular function maximization problems. Now, when you have a Polymatroid function, or for that matter, any monotone function, maximization is trivial since you just take the largest one, right? And that's sort of easy. So it really only becomes interesting when we add constraints to the problem. Unlike submodular function minimization, it's already, it's interesting when we do unconstrained minimization, unless of course it's a Polymatroid case. In the submodular function maximization case, we would say find the maximum under some constraint, like a budget constraint or a size constraint, or we would want to find the maximum under a non-Polymatroid version of the problem, or do both. Now there's a lot of different types of constraints, and we're going to consider some of them. And of course there's a dual form of maximization where you sort of want to find a minimum cover problem, and that's basically like the dual of a maximization problem, as we will see, is going to be a problem where you want to choose a small set of elements that has a certain quality assurance, a quality guarantee, or coverage requirements. They're all basically the same idea, which we'll do that. So let's sort of define what we're doing. Here's the set cover problem. So let's say E is a set of ground sets, and E1 through EM is a set of subsets. This is not necessarily a partition, so there can be overlaps of the subsets. And then V is I guess V is really our ground set. It's the set of integers, and it's the set of the integers index these subsets of E, right, which are these guys. And we're going to define a submodular function, and which we know to be submodular, based on essentially the size of the union of the E's that are indexed by the set X that we've chosen as an argument of the function F. Okay, and F, as maybe hopefully is very clear to you, is the set cover function, right? So this is the function that measures the degree of coverage of E based on the set of indices, or the set of subsets that you're using to cover E. F is always monotone and submodular, and so therefore it's a Polymatroid function. And so the set cover problem basically asks for the smallest subset of V that achieves coverage. So basically we want to find the minimum size X subject to f of x being greater than or equal to the size of E. Now you might say, well, why do we say greater than or equal to it? I mean, it doesn't really make a difference, right? Because obviously you can never be greater than, and so the constraint, the feasibility says you can either be equal to E or greater than or E, but since there's no solution that can be greater than or E, we could equally say that that's equal to E. It doesn't matter. And we might want to also use a more general modular function, like we might have a cost associated with individual elements that aren't uniform. Like cardinality just says everything costs the same. And here what we're doing is we're trying to find a minimum modular cost subset such that there's a quality constraint or coverage constraint. And so then we could use a modular one. Now it turns out that this was shown, just the set cover already, even though this is a special case of submodular function minimization, this problem was shown to be NP hard in 98, and moreover showed that you can't approximate it better than log n unless NP is just very, very slightly super polynomial, right? So even the cardinality constraint submodular function maximization is hard, and it turns out that most of the submodular max problems we're going to see, even these simple cardinality constraints are going to be NP hard, but that doesn't mean it's a showstopper. Like unlike submodular minimization, we said it's polynomial, but to do it exactly, it's like n to the 6th, right? So that is a showstopper. For doing approximate submodular max, it turns out that there's going to be relatively cheap, low order, inexpensive, scalable to large scale problems, algorithms that can give us a pretty good quality approximate solution to many submodular max problems. And so, maybe, in some sense you could say, for practical reasons, submodular maximization, even though it's NP hard, is easier than submodular minimization, which is polynomial, right? Because I once talked to someone at Google. I see some of you are wearing Google shirts here. And someone at Google said, well, we're not interested in algorithms that are more expensive than linear. You know, n log n, that's no good. That doesn't work for us. If it's linear, we'll take it. If it's n log n, forget it. So that's sort of the extreme, basically. So here we've got a polynomial n to the sixth algorithm versus an NP-hard problem whose approximation is like n log n. So I still think that that's pretty reasonable. And actually, there's some work recently that shows that you can get it better than even n log n. But here's the max k cover problem. So this is the combinatorial problem corresponding to the dual of the set cover problem. So again, we've got a set of subsets. We've got a set of integers that index the subsets. We have a submodular function corresponding to the set cover problem. It's still the set cover function. And in this case, the max k coverage problem basically says we want to maximize the set cover problem, set cover function subject to a size constraint. So given that we have a budget of k, it says I can't afford to spend any more than k dollars on this particular subset, what's the most coverage we can do? That's the max k cover problem. So that also is NP-hard. And it can't be approximated with a ratio. This was shown again by that same paper. You can't do better than 1 minus 1 over e. So you can't do 1 minus 1 over e minus epsilon. It's impossible. Now, and this is already for special case. So this basically means that if we were to use a submodular function in place of the set cover function, this would immediately be NP-hard, since we're showing a special case is NP-hard. So now we're given an arbitrary polynomial function. And again, so the goal here is to do this, is to find the maximum value of the submodular function subject to a cardinality constraint. And since it's a Polymatroid function, we're free to just choose sets of size k, right? Because if we choose a set of size k minus 3, we can just keep adding elements. And sure, maybe it flattens out, but it's not going to get any worse. We can afford k, so we can always spend what we afford. And here's the classic Nemhauser algorithm, which I think some of you probably had heard about even before taking this class, because it's received so much attention in the machine learning community of late. And here we are, very near the end of class, finally talking about this, right? So this result says that for normalized submodular functions, the greedy algorithm, which it's basically still Edmonds' greedy algorithm. So I have another anecdote. So I know that George Nemhauser was greatly inspired by Jack Edmonds. I like Jack Edmonds. You might have guessed. But so I've heard many interesting. When I met George Nemhauser, he was telling me interesting stories about Jack Edmonds and how he was so inspired by Jack Edmonds. So I don't know. It all leads back to Jack Edmonds, some way or another. But anyway, it's approximated by the simple greedy algorithm. And the simple greedy algorithm is basically finding a total order, or at least an ordering up to k, where the ordering is based on choosing next whatever looks best. Right? So it's basically saying, and that's not like you have some, like in the Levast extension, where you've got a weight vector where you're sorting the elements based on the weight vector. You're just basically choosing whatever next maximizes the submodular function. This is the same thing that we used, basically, except here now the function evaluation is itself choosing what next to use, not the weight vector, which is what we saw before to either compute the Levast extension or finding the maximum independent set in a maximum weighted independent set in a matroid, or to find the vector rank function. All of those things which use the greedy algorithm that we've seen. And here's the actual algorithm. So basically the greedy algorithm is very simple. We choose v. So we just repeat the ground set number of times. We choose v from amongst the set of elements that we haven't yet chosen, the one that maximizes the gain. All right. And since we're subtracting off a constant at that point, we can just choose whatever one that maximizes the valuation. So we can consider adding v to all of the current sets that we've got now, which is si, and then when we're done with that, we choose one of those guys, breaking ties arbitrarily, and we just add it to the set. This algorithm has a guarantee, and that guarantee is the famous 1 minus 1 over g guarantee. So the precise statement basically says that consider, this is for any I, right? So consider the maximum over all subsets of size up to and including I, and you multiply that by 1 minus 1 over e. Okay, so what is 1 minus 1 over e, by the way? That's approximately 0.663 or 63. 0.63, I think it is. 0.63. So you're going to do about 63% with the greedy algorithm in the absolute worst of case by just choosing the greedy algorithm. So the greedy algorithm at up to set I is going to do, in the absolute worst case, 63% of the best you could possibly do. And that's a really good guarantee. So that's a constant factor guarantee. It's basically true irrespective of the ground element, irrespective of the submodular function that you're using, irrespective of the submodular function. It can be matroid rank, it can be grouped, it can be this crazy function that we put on the board. It can be anything. Okay. And then to do this, we just repeat that greedy step. Right? It's just very simple. And it generalizes the max K cover. And moreover, it's tight, right? So Feige said that this can't be improved unless P is equal to NP. So in other words, Feige said that the 1 minus 1 over guarantee, even for the set cover, it's not possible to do better in polynomial time. So even though this greedy algorithm is only doing, this simple procedure, you can do n to the 10th operations, and you're not going to get any better. There's no point in looking for a more expensive, like submodular function is n to the 6th, submodular function minimization is n to the 6th. There's no point in, say, searching for a higher order polynomial time algorithm for this problem. That's very powerful. So here's the intuition for why the algorithm works, and what we're going to do is prove it, because the proof is actually very simple and it uses properties that at this point everyone should be very familiar with. So basically what we do is greedy chooses at each step. I think I think there's a couple of changes I made to the slides that I think might lead to a few typos. So this is I plus 1 here. So we're going to choose Vi plus 1 to maximize this quantity. And let me just go back for a second. Yeah, I mean, I've got to change these slides a little bit, but there's going to be a little bit of mix-up between the VIs and the VI plus 1s. What I like, when I wrote these slides originally, I was sort of thinking that VI would be the one that's added to the SI, but now what I think is better is if VI plus 1 is the SI plus 1th set. So let's just go with I plus 1 here. So greedy basically chooses VI plus 1 to maximize this quantity. Okay, although the algorithm just called it VI, but that shouldn't be unclear to anybody. Hopefully. Is that unclear? We're just renaming that element. Okay, so now S star is the optimal solution of size K. And then let's say that opt is the valuation of whatever that optimal solution is. And what we're going to do is we're going to show that submodularity is going to guarantee us that 1/k of the difference between the optimal valuation and the current valuation is going to be a lower bound of the difference between the valuation, the next valuation, and the current valuation. In other words, if this is saying that there exists a V from amongst the elements that we've not yet chosen, which is such that if we add it, the gain is going to be no less than 1/k of the way to the optimal from where we are now. Okay. And interesting, so I just wanted to give you a plot. So this is a plot of the horizontal axis is K. It's a plot of this function. It's basically 1 minus 1 over K to the kth power. And it asymptotically approaches 1 over E. And it's always upper bounded by 1 over E. Okay. So what this guy does, once we've established this, then what we're going to be able to do, so equation 19.21, which is coming up in a couple of slides, is going to guarantee that 19.12 ensures that the opt minus the next set that we've chosen is going to be less than or equal to 1 minus k times opt minus the ith set that we've chosen, which then we do a little bit of algebra. It basically says that opt minus the current set is less than or equal to 1 minus k over k, 1 minus 1 over k to the kth power times opt, which then is upper bounded by 1 over e times opt. And from that, we get the solution. And it's basically just algebra. So this is the solution we've got. So let's just go through a little bit of it. And we're going to use submodularity in a couple of places. Okay. So let me just add a little bit of other stuff to this. Okay, so equation 19.21 will show that 19.12 implies that stuff below it. Okay, let's do it. So here's the actual theorem. We're going to prove it a slightly more general theorem. So we're going to say, let's say we've got a non-negative submodular, monotone submodular function, and this guy S is going to be the chain that's formed from the greedy algorithm. So there it is, a chain where you have a sequence of sets, right, which form a chain. So the successive sets in the chain are subsets of each other. And then what we're going to do is, for all k and l, which are strictly positive integers, we're going to find that S of L, where S of L is again the set element in the greedy chain, is going to be greater than or equal to 1 minus e to the negative L over k of the max you can possibly do of size k. And in particular, if we set L is equal to k, we're going to get the 1 minus 1 over e guarantee. Now what is L and what is k? So k is the size of the optimal solution of size k. Right, obviously. That's what k is for. So we're assuming that opt, when we use opt, it's going to be the best we can do of size k. L is the point that we stop the greedy algorithm. So like we could, what if we want to get the solution of size k? Like what if, like for example, there's a quality assurance there's a quality that is only achieved of elements of size k, and then let's say that a factory manufacturing plant says, well, you have to get this quality, and in order to do so, you've got size k, but we have a particular budget, and you might come in and say, well, if we choose k halves, we can get this quality, and so we set L to equal to k halves, and what's the worst case you can do with a set of size less than k, or even larger than k? You could choose L to be bigger as well, and you'll see a bound in that case. And really the question is, how well does a set of size L do relative to the best of size k? And so the bound is a little bit more general. And it basically says this is the relationship. And so how do we prove it? Well, we're going to fix L and k. So L is the number of items that we're ultimately going to choose, and k is the set of items that what we want to compare against, the optimal case. And let's say that S star is the best solution of size k. So this is the classic proof, right, of the 1 minus 1 over e proof. Are you all anticipating? Are you excited? This is where 1 minus 1 over e comes from. Ready? So we're assuming that S star is equal to size k, of course, so the optimal solution. And let's just order the optimal solution arbitrarily. Doesn't matter. Just choose an order. And let's say that this is the greedy order chosen by the algorithm. So so V1 through Vk, actually I think this should say L, and this should be equal to S sub L, right? So it's an ordering of the elements up to size L that were chosen, which is going to be equal to SL. But it just allows us to talk about elements up to size L. Okay. So we're going to start we're going to assume that I is no greater than L, or I is less than L. We're going to start with f of S star, and that's thanks to the polymatroidal property. That's less than or equal to f of S star plus or union Si. And then this is just taking the chain rule. This is the chain rule of submodularity by looking at the conditionals. And we're just taking that order of the optimal solution. Doesn't matter again what the order is, and we're just adding and subtracting. It's telescoping sum. Everything but the first and the last cancels out, and we're just left with that guy. Now, thanks to submodularity, we can essentially just remove all this stuff which I'm marking in red, and that's going to make it an upper bound. Right? In 19.16, we've got an upper bound. And we're summing here over all elements in the optimal solution, right? But now, if we place that element V with v of I plus 1. So basically that's always going to be an upper bound because the greedy procedure always chooses the max at the current point, right? What the greedy procedure says is what? When your current state is Si, vi plus 1 is the next one we're going to choose, right? So therefore we've got that upper bound. But now what we've done is we've divorced the index of the summation from the actual term. Oh, actually, before we do that, so let's write it this way. So we can also write it in this fashion, right? Where, you know, this thing here is equal to that thing here. Right? It's just by definition. Because S of I plus 1 union S of I is just the same as S of I union V of I plus 1. And now what we've done is we've divorced the index from the terms in the sum. So we can say, well, there's k terms in the sum, and so we've got k here. It's k times f of S I plus 1 given S of I. S of I. So what we get then is the equation that we saw before, 19.12. So in other words, we get, when we combine this guy and this guy, we get this, and that's going to be less than or equal to k times this, which then we can write it in a slightly different way. It's just by expanding this. And that's exactly equation 19.12 that we saw a couple of pages ago. Okay. So let's define delta I to be the difference between the optimal solution and the current solution. Okay, so this is sort of like how far we have to go to reach optimality. And so if we take a difference of deltas, then we just get the difference of the elements evaluated at the chain because the optimal solution is going to cancel out in the difference of the deltas. So what we can then show, I mean, from what this is saying here, if we look at this is delta of I, which is less than or equal to k times delta of I minus delta of I plus 1. Right? And that's exactly this. And then doing a little bit of algebra, we've got delta of I is less than or equal to 1 minus 1 over k delta of I plus 1 is less than or equal to 1 minus 1 over k of delta I. And so I and we can sort of create this cascaded chain of these inequalities, and what happens is that we're multiplying 1 minus 1 over k to the nth power. And so we've got a relationship between the very first delta and the current delta, the nth one. Now, the function is presumed to be normalized, right? Or at the very least, it doesn't have to be normalized. Like it's monotone. It's monotone non-decreasing. So when we subtract off f of 0, that's going to be equal to f of s star, right? And that's, I guess it's because of the non-negativity. That's really what I should be saying. So non-negativity. And then we use a variational bound, which is the standard 1 minus x is less than or equal to x to e to the negative x. This is a well-known bound. And we get that starting from this, we use that, and we're setting x is equal to 1 over k. And then we use that bound, and so what we end up getting is delta L is less than or equal to e to the negative L over k times f of the optimal solution. And then we identify and we look, delta sub L is in fact just this difference. Going back to here, we get this bound. A little bit of algebraic rearranging, and we get essentially what we're trying to find. Okay, so that's it. That's the proof. I mean, it's a very simple version of this proof. Now, so let's just review. So what was critical here? The real critical thing, where submodularity comes in, we used the submodularity and the greedy, right? Submodularity is used in this step. Let's use a different color. Submodularity is used in this blue step. And then greedy is used in this gray step. And that's all, that's when it's really been used. The rest is just pretty much algebra, I think. Now, how good are these bounds? So here's the actual value with a couple of additional significant figures. It's 0.63, so it's about 63% of the best you can do. But on the other hand, with this L thing, like what if we wanted to guarantee a solution no worse than 95% of the best, where the best is the best of size k, like how big would L have to be? So we just set 0.95 to this quantity and solve for L, and that's going to give us L has to be 4 times as big as k. So to get 95% of the solution guaranteed, you choose, like if you want a set of size k, but you want to get 95%, you would choose a set of size 40. I don't know, is that good or bad? What if you wanted something like 99% or like 0.99%? So then you would choose a set of size 7 times k. Okay, so that's basically 7 times k is going to guarantee you it. Now it turns out that in practice, you almost never see this worst case. This is the absolute worst case. You have to have very, very contrived submodular functions, very strange submodular functions that almost never come up in practice to achieve these worst case bounds. And I don't think I'm going to talk about this today, but there's a notion called the curvature of the submodular function. And the curvature of the submodular function is a property of a particular submodular function, and if it's the case that the function is not too curved, the worst case bound gets much, much better than this. Because there are a lot of sort of pretty strong assumptions that we're making here in this proof that for most functions of interest, like square root of modular functions and things like that, don't have this bad guarantee. On the other hand, I should mention that the matroids are amongst functions that can achieve this worst case. Well, I should say grouped matroids have that property. So if you take grouped matroids together, then you can get the worst case just from grouping matroids together. What about matroids, actually? What I said before was not correct. So let's ask that question again. So if you run the greedy algorithm with matroids, what happens? Well, it's a matroid rank function, right? Yeah, we're going to get if there is a size independent set of size k, we're going to get it, right? So matroids are going to be exact. So interestingly enough, even though matroids are complex in certain ways, from the perspective of finding an independent set of a particular size, we're going to get it, right? Because we just keep adding independent sets. And because of the exchange property of the matroid, when we use a matroid rank function, what I said before was wrong. Actually, matroids have exact solutions. If when we group the matroids together, do we get the approximate solution, the worst case approximate solution? Because we're greedily, if there's an independent set that's of size bigger, there's got to be one that's, remember, all maximal independent sets of the same size. And because of the exchange property, if you've got an independent set that's smaller, you can always take an element from the larger one and add it, which means that if you're not at the maximum size independent set, but you're independent, there always has to be one other element that will increase the rank by 1. And greedy will choose that maximum element. Hence, greedy is optimal. Okay, what about running time? So the greedy algorithm, as we've stated, runs in n squared time. But n squared, as I mentioned, is not practical to some whose names are written on some people's shirts today. Greedy, however, can be made much faster by a simple strategy. And submodularity can be used again to come up with an algorithm which still has exactly the same guarantee. It has exactly the same result, but it's much faster. And this is called the accelerated greedy strategy. And it's been rediscovered a couple of times. One name that's commonly used for is called the lazy greedy algorithm. But the original procedure is from '77. It's the accelerated greedy algorithm. Okay. There's people here in this university who rediscovered it. Some of whom I happen to be friends with. So we describe it next. We're going to describe this procedure. So here's how it works. It's actually really cool. It's really neat. And it's actually recently been discovered, interestingly enough, completely independently. This is something that I've only found out recently myself. And well, I discovered that it had been discovered independently in the machine translation community, believe it or not. That somebody came up with an algorithm that turned out to be submodular, although submodularity was not mentioned in this work. And they had this very, very complicated algorithm for optimizing this discrete function, which turned out to be the accelerated greedy algorithm. But they just said, oh, I think this makes sense. I don't know anything about it, and it seems to be intuitive sense. But it turns out that they unintentionally used submodularity, and they unintentionally rediscovered Minot's algorithm, strangely enough. So there's something very natural about submodularity, I think. This seems to happen over and over again, that people sort of unintentionally utilize and discover submodular properties without realizing that there is this whole mathematical study of the functions, which to me, as I've said early in this course, it adds evidence to submodularity's naturalness for many problems in machine learning. But anyway, let's talk about this accelerated greedy algorithm. So at any stage in the algorithm, we've got essentially a set of gains, right? So you can think of it as like we've got an array or something which stores these current gains. And let's just go ahead and store them in a sorted priority queue. Priority queue basically means that they're automatically sorted, and then when we can do a pop from the priority queue and we're going to get the maximum one. We can do a query from the priority queue to ask what the maximum one is. And what we can do is we can pop an item off the priority queue, readjust it, and then stick it back in the priority queue, and the priority queue will very efficiently percolate it to the appropriate spot in the queue. And let's assume, and this is quite possible, so there's an order 1 operation to find the max, because it keeps it in that structure, and it's log n to insert it in the right place. Okay, so we take the max from the priority queue, and then what we do is we update S. Okay, so Si becomes Si plus V, where V is the item that achieved the max. Okay. Now, thanks to the fact that the function is submodular, that for any element that we haven't yet chosen, so Si plus 1 is the new set, so any V from amongst the ones that we haven't yet chosen is such that the new set, S of I plus 1, is going to render V less valuable than it was in the old set, because these conditions, these contexts are growing. But we have this whole huge priority queue that's organized around this old set, S of I. But now what's happened is that once we've created a new S of I plus 1, what happens is that all of these old items in the priority queue are too big. They're all upper bounds of what their true valuation should be, thanks to submodularity. So all of these guys are out of date. In some sense, they're stale, but they're all upper bounds of what their unstale value should be, or what their fresh value should be. So if it is the case, then that somehow we do find a V prime such that the gain of V prime given the new set Si plus 1 is greater than or equal to alpha sub V, and let's say that alpha sub V are the potentially stale values sitting in the priority queue, then basically based on submodularity, we know that this is plus 1 here. We know that basically we're going to be bigger than, if we just have this property, we're bigger than all the elements in the priority queue, which are equal to this value. That's the stale value, which is going to be bigger than their true value. So just by finding a new maximum value, we're bigger than all of the previous values. even though we've never even evaluated them, because they're all upper bounds. So what the strategy is that we actually find the maximum guy in the priority queue. So let's say we take it off the queue. Take it off the queue. And maybe it's stale perhaps, but then maybe we freshen it up. We really evaluate it. We compute this new gain. And if its value is still at the top of the priority queue, because we can actually check the priority queue and check its new max. And if it's bigger than the new max, then we've got the true max. And we're done. We don't need to bother to reevaluate all of the other elements that are sitting on the priority queue. On the other hand, if it isn't bigger than the previous one, we just replace it in the queue. We sort of push it back on to the queue, which is log n, which has log n costs. So this procedure, again, thanks to submodularity, is exact. It has exactly the same 1 minus 1 over e guarantees as the n squared algorithm. But in general, it runs much faster. So, I mean, it has been shown to run over maybe 700 times faster. In the very best of cases, it has a speed up of, I mean, the old algorithm is maybe nk, the new algorithm is n plus k. And then the reason why it's n plus k is because you always have to do some initial evaluation by building the priority queue. But there's a log, I mean, this is ignoring log n factors. But then each one of the elements that you choose, k, that's under the assumption that each one you're choosing happens to be the max. That's if you're really lucky. That can happen. I mean, if your function is like modular, that would happen, for example. But maybe you don't know that your function is modular. So this has been rediscovered. I mean, it's independently rediscovered, I think. And so Leskovic and Andreas and Carlos they just rediscovered this in 2007, and they call it the lazy greedy algorithm. Okay. And then this is actually pretty good. I mean, n log n is scalable to very, very large data sets, and so document summarization and finding blogs of interest. And there's all sorts of great applications of this that scale to very, very big data sets, and it's possible to do it even more. So anyway, let's talk a little bit about the priority queue structure to make this more precise. Did you have a question?
You might explain it. I was going to ask how it was n log n and that's where.
Oh, it's empirically n log n.
Oh.
Empirically. This is just, I mean, in the best of cases, it's nk. But basically, when you run it, it seems to be n log n. I mean, it depends very much on the function, right? Like, you could get really, really unlucky. But in practice, that doesn't happen. So basically, you have a priority queue with the data structure, and you have several operations. So you can insert. So basically, you have an item, which is a ground element and a value, alpha. And so you can insert into the queue the value and the item and the value. You can pop an item off the queue. So the insertion is going to be log n time. Popping is order 1. And you also have querying the max value. So those are the only things that you need for your priority queue to have. These 3 things. A log n insert operator, order 1 pop, and an order 1 query of the max value. And so in the algorithm which I'm about to give you, we're going to use this term fresh and stale in some sense. So an item, when you pop an item off the queue, it's fresh if it's true values, if its valuation alpha is the gain from the current S. And it's stale if it's the case that the current S is bigger than the value that it's evaluated at. Okay. And so what we're going to do then is we're going to store an extra bit. We're going to use an extra bit to store whether or not the item is stale or fresh. So if we pop an item and it's fresh from the queue, then it must be the maximum. And the reason why this can happen is, so what happens is the following. It's like you pop an item and it's stale and you stick it in, you pop an item and it's stale and you stick it in. As you keep popping these items that are stale, that are not the maximum, we'd stick them back in the queue, and what can happen is that at some point, all these items that, all these items are getting smaller, right? Because every time we evaluate them in the larger context, they're going to get smaller. So all these items that were bigger than it, all these stale items that were bigger than it, once they're fresh, might get smaller than it. So that what might happen is that we might eventually get to this point where we pop an item that's fresh. And as soon as we pop an item that's fresh, which is from the top of the queue, we're guaranteed that that's the maximum item. And in practice, it's almost never the case that you need to go through and do this for all items, for all order n items in the queue. So here's the algorithm. So here's the order n, the guaranteed order n property. It's really n log n. And then all this other stuff, the loop at line 4, tends to not be n squared and tends to be empirically n log n. Or sometimes it's even faster. It's like less than n log n. It really depends on the function. But basically what you do is you repeatedly pop stuff. And if it's not fresh, then you just recompute it so that it becomes fresh. So then you check in line 8 that if the popped item was fresh or it's greater than the maximum item, then you set it to the, you add the item. That becomes the maximum one, and you set I plus 1, and then it's gone now. It's no longer considered in the queue, and then you repeat. Okay. If it's not fresh, or if it's not greater than the max, then we just go ahead and insert it. So basically, what's happening is that this percolation back up stuff, like if we repeatedly do this, and then this, and basically what's happening is we keep getting stale guys, and they keep getting stuck back into the queue. And that green stuff is the thing that potentially, in the worst case, could potentially run n times, if you're really unlucky. Hopefully not. And you do this whole stuff until you've gotten a total ordering. Or you can always stop once you've gotten L items that you need. You don't have to run the total orderer. Okay, so then any questions about the accelerated algorithm, or the lazy algorithm, whatever you want to call it? Does that make sense? Okay, so interestingly enough, so the dual problem, the submodular set cover problem, the submodular cover, is basically where what you want to do is you have like a quality assurance guarantee, which basically says alpha, you're not interested in any set whose valuation is less than alpha. And so this is really like a quality assurance. Like F might be quality, and feasibility means that the quality of any feasible set must be no less than alpha. But amongst all sets that are feasible, you want to find the one that's smallest of size. And so therefore it's called the submodular cover, or submodular set cover. Now, there's a simple way of turning it into a problem that looks like this. And what we can do is then we can always take alpha to be equal to f of the ground set. So remember, f is a Polymatroid function. We can create a truncated version of that Polymatroid function whose value is saturated at alpha. And so we have an equivalent formulation by saying, find me the smallest set such that f prime is greater than or equal to f prime of v. So sometimes when you see this problem, it's not written in terms of alpha, it's written in terms of f of v, but there's no loss or gain in generality between 19.29 and 19.30. They're identical specifications. Again, thanks to this truncation trick. And the fact that it's a Polymatroid function. And so you can see that the submodular set cover generalizes the standard set cover, where the submodular function is the set cover function, which is submodular. Now, how do we solve this? We said in some sense this is dual. I mean, this is dual to the max k cover problem, or the problem we saw before, because there what we wanted to find was the maximum valuation subject to a size constraint. Here we want to find the minimum size subject to a quality constraint. So what algorithm solves this? It turns out that the very same greedy algorithm solves this problem. And what we do is we run the greedy algorithm, and we keep running it until we find a set that achieves the quality constraint. Okay. Now the nature of the bound is slightly different. It's not constant factor in the same sense, but what we've got is if the case that the submodular or the polymatroid function is integer valued, then the bound is going to be a log max value, or sometimes it's written as the harmonic number, but basically it's going to be something that's related to the maximum value of the singletons of the submodular function. And in general, it's hard to approximate better than log of alpha. There's a couple of different variants of the way the bound is, but in general, these bounds are not in the same form. They're not constant factor in the sense that they're unrelated, completely unrelated to the function. Okay, so let's summarize. I think this is just a summary of what we just said. So monotone submodular maximization only makes sense when there's a constraint. We talked about the cardinality constraint so far. There's the generalization of the max k cover and also the set cover problem. The simple greedy algorithm gets this 1 minus e to the negative L over k approximation, which turns into the famous 1 minus 1 over e. If you were to have a shirt that sort of the submodular shirt, it should say 1 minus 1 over e. And if you were to walk down the street and everyone would say, what does that shirt mean? Then you can say, oh, this is the famous submodular inequality. That's also one of the things that we have floating by in that opening musical ridiculous thing in our YouTube lectures, right? This floating 1 minus 1 over e, right? It's the flying spaghetti 1 minus 1 over e. And then, right, we've got submodular cover, and then of course Minot's acceleration trick, which works really well. And in practice, when you implement this, when you want to implement this, you would do this accelerated trick. Okay, any questions? Okay, so there are lots of other types of constraints that you might want to use. Like, one thing that's very interesting and very important for applications is doing submodular maximization subject to matroid independent set constraints. So matroids are very powerful, and you can consider multiple matroids as we've seen, and the independent sets of a matroid might be seen to be a reasonable constraint. Like think about the k-uniform matroid. So the k-uniform matroid are matroids whose independent sets consist of all sets of size up to and including size k. So basically the cardinality constraint is a matroid constraint already. And so we have this problem maximizing the submodular function subject to the set being an independent set of the matroid. We've already solved the special case of that. But now there should be no confusion. The matroid is completely different than the submodular function. Here we've got a polymatroid function, which is not a matroid rank function, and we've got another matroid which is completely separate, and that the independent sets of those matroids define the feasible sets that we're interested in. So what we've shown then is that the greedy algorithm gives you this 1 minus 1 over e approximation for this very special case of a matroid constraints, the k-uniform matroid constraints. But what about arbitrary matroids? Like, for example, partition matroids, or transversal matroids, or dual graph matroids, or some of these combinatorial geometry specified matroids that are non-representable. I mean, there's lots of matroids, and as we saw, or as I hope to sort of convey to you, matroids are very powerful. And then another set of constraints are knapsack constraints. So a knapsack constraint basically says that you've got a non-negative modular function. So every element has a cost, which is a non-negative value. And then the knapsack constraint says that feasibility means that the sum of the weighted elements can't be greater than b. So can you represent this with a matroid? So think about this. If there's a matroid, then it must be the case that all maximal independent sets are the same size, right? Now, an independent set, the only way to make this sense in a matroid is like an independent set So script I would be equal to the set I subject to C of I is less than or equal to B. Is it possible? So this is script I here, and this is, regular I. So is it possible I can have different independent sets of different sizes, different maximal independent sets of different sizes? Yes, absolutely. I could choose one. There could be one guy that one element which is very, very costly and already matches the budget constraint. That's an independent set of size 1. And then I could have another independent set which is lots and lots of really cheap elements. But anytime I add anything else to that set, it's no longer independent. So therefore, this is not a matroid. So knapsack constraints seem to be fundamentally different. But on the other hand, that's a very simple form of constraint. It's kind of like saying, well, each item has a cost. Like, like if I'm doing document summarization, the cost of I'm choosing subsets of sentences from some document. Should I charge long sentences and short sentences identically? No. Long sentences should cost more. They take up more real estate. They're more bytes. They're more screen real estate. If I want a summary that fits on my iPad screen at 7-point font, because that's the smallest I can read, I want to charge long sentences more than I charge short sentences. So knapsack constraints, therefore, are important. So on the other hand, we might be able to do some fun things with multiple matroid constraints. Like, I want to be independent in the intersection of a bunch of matroids. So any feasible set is independent, or in other words, any feasible set is independent in all matroids. Or some combination of the above. I might want to have a couple of knapsack constraints and a couple of matroids, and we might have a big knapsack matroid kumbaya party, right? All sort of, gathered together in peace, expressing their desired constraint on the submodular optimization problem, right? So these are all problems that are conceivably useful in machine learning. So now one obvious way of doing this, and I think the only algorithm we're going to be able to get to today is, by the way, today's the last in-person lecture, isn't it? So there will be another lecture, actually on YouTube. So I won't be able to, well, I guess you will probably ask as many questions for the YouTube lecture as you are doing today. So maybe it won't be that different. But anyway, so one obvious heuristic. I don't want to keep you late today because I kept you so late on Monday. But one obvious heuristic is basically just to use the greedy step. Let's say we want to do multiple matroid constraints. We could just run greedy, and as long as we're independent in all the matroids, we keep adding elements. But as soon as we get to the point where any addition is such that we're no longer independent in one of the matroids, we stop. So that's exactly what 19.31 does. It basically, let's zoom in on this constraint guy, it basically says here, from amongst the elements that we haven't chosen, choose one such that when we add it to the current set, this is, we are independent. That is, we're in the intersection of, so this should be, if this isn't clear to you, what this should be looking like is this. There's a bracket around here, right? So Si plus V is in the intersection of the independent sets, okay? So we choose next whatever feasible element looks best. This actually also has a guarantee, interestingly enough. Again, thanks to submodularity and the property of a matroid. You wouldn't have a guarantee if either it was the case that they weren't matroids or it wasn't a submodular function. But the guarantee is not so great. Right? The guarantee basically is 1 over p plus 1. So where p is the number of matroids. So we've got p matroids here. So that basically means the more matroids you add, the worse and the worse and the worse the guarantee. The guarantee is going to go to 0, so meaning that you're not going to do good at all. Now the question is there a 1 minus 1 over e guarantee for this, which is independent of p? So this algorithm, this very, very simple algorithm, doesn't do it. But there are, as we will talk about next time, algorithms for doing it. But on the other hand, if there's one matroid, if there's only one matroid, maybe this is a very simple, quick and easy way of doing this. You get a 1/2 guarantee when there's one matroid. And moreover, what's nice about this algorithm is that the accelerated trick still works. We can still, anytime you're doing greedy, you can do acceleration. Because again, what you're doing is you're choosing next whatever feasible element looks best, and thanks to submodularity, your feasibility check, when you pop an element off, either you're feasible, but thanks to the fact that it's a matroid, if you create a circuit with that element in any subset, you're also, in any future superset, you're also going to create a circuit. So once you've found an element that when you add it creates a circuit in one of the matroids, you just toss that element away. In the accelerated algorithm, you can still do that very easily with priority queue. Okay, so the bound's not that good when there are many matroids. So what we're going to do next time is, and I'm sure everyone's going to watch this lecture, this next lecture, we're going to talk about some algorithms that can do better, and also talk about some other forms of submodular max under different constraints. But one of the things I want to say, since this is the last time I'm going to see you, by the way, we had these evaluation forms, and I forgot to bring them, so I'll have to do them next Thursday. So we will meet next Thursday for our final projects. I'm going to be trying as hard as I can to respond to any comments on Canvas as soon as possible. I know that there are some very good questions, and thank you for asking them, and I hope that I answered them faithfully and usefully, and I know that this is important for me to have a quick, so I will try really diligently to respond as quickly as possible. B, the next lecture on YouTube probably won't happen until after the NIFS deadline, because I'm going to be, but I will try to get it out by next Thursday. I don't expect you to watch it, and who knows what you're going to do. So one other thing I wanted to say. Oh yeah, the last thing I wanted to say. So again, I'm slated to teach a submodular optimization class again next winter. And I was thinking, this is the shortest amount of time between instances I've ever taught this class. So I was thinking next winter, what I might do is carry on, and maybe do half of the quarter as like in this format, because there are some things that I haven't gotten to, but then the second half of the quarter, each one of you would come up and do a paper reading, and we would read some advanced stuff. So this would be like part 2. Some of you have asked about a part 2, like advanced submodular structures in machine learning, and we'd read some recent papers. And this might be fun. It would be a little bit more informal, but that's what I might do. So if there's interest, hopefully there is some interest. Hopefully I've given some of you some interest in submodular functions. Maybe we'll do that in winter. But in any event, good luck on your projects. I hope everybody has a successful time, and I hope everybody wins. And right, everybody gets exactly 3.8236 seconds. But if you get like 1 millisecond faster, then sorry, that's it. You don't win. And good luck. So see you on Thursday.